All right, this video is to address function operations. Basically, there are two ways to denote function operations, or the four functions that we're going to look at. Addition, subtraction, multiplication, and division are kind of your basic four functions. Normally, you can write them just as f of x plus g of x, so writing that there are two functions and putting the symbol in between. And you'll notice we can do that for all of the other functions as well. Multiplication, remember, is your solid dot. Subtraction, of course, is a minus sign, and division, of course, being a fraction. Now you can also write them just as the two functions related together, both of which happen to be functions of the same variable. So notice up here in addition, we can say f plus g, saying add the two functions, but they're both functions of x. And the same thing goes for multiplication, and again, no symbol needed. If there's nothing there, we assume multiplied, f minus g of x, or you can say f divided by g of x, all of which are still that same statement. You're adding two functions or subtracting them or multiplying them. We'll also deal in this section with some power functions. Basically, a power function is a one-term function where you can change that exponent as well as the initial value. Could be a polynomial, such as 4x cubed, but it also can have fractional exponents, so we'll have to deal with things like roots. And finally, in here, we'll also talk about domain. Remember, domain we've talked about before, but it's what you can plug into a function and still get answers back in the resulting function. Such things that could go wrong with that would be in quotients, thinking about division, we can't divide by 0. Or if you take the even root of something, remember that we have to take the even roots of only positive numbers or 0. You can't plug negative numbers into even roots and get real answers back. Along those lines, kind of as we're talking about domain, again, it's the set of numbers that can be substituted into a function that provide real outputs. So if you're talking about a linear function, you can always multiply or subtract. You'll get all real numbers that you plug in will always give you real answers back. Same thing goes for squaring things, multiplying by a negative, taking the odd root of something, x to the 1/3 down here in the lower left. You're going to get real answers back. However, with square roots, remember that our domain would only be all non-negative real numbers, or as we would often say, x just needs to be greater than or equal to 0. And then for division, basically any number works except for 0. Remember, you can't plug in 0 into the denominator of a function. So how that ties together with this section, we're going to be asked to do a few different things, such as find the sum of f of x and g of x. So what you're going to do there is just add together, again, two ways to write that, f plus g, both of which are functions of x, or we could say that that's f of x plus g of x. And again, that's what we're trying to find. What I would probably do is just write down all my terms. So I'm going to write down 3x to the 1/3 from the first function, and it's also going to have a minus 4 when we get there. And then from g of x over here, I'm also going to have a 2x to the 1/3 and a 5x and an 8. So let's add our like terms together. 3x to the 1/3 plus 2x to the 1/3 makes 5x to the 1/3, or 5 the third root of x. We've also got a term with just an x in it, so plus 5x, and negative 4 plus 8 gives us a plus 4 at the end. So that would be our function. Now at the bottom here it also says find the domain of f plus g of x, the domain of what we just found. Well, remember, taking a good look at our function, you can take the third root of anything. You can always plug whatever you want in there. We've got a few things multiplied and added, but none of those operations ever have a major issue as far as domain is concerned. So I would say the domain of f plus g of x is going to be all real numbers. Now, one thing that we do want to check as we're talking about this is that the original functions f of x and g of x also allow us to use anything we want. Sometimes when we do the operation, we cancel out things that used to be a problem. So we'd have to take a look up here. But again, third roots and multiplying and subtracting, third roots and multiplying and adding, nothing in f of x or g of x individually is a major problem. So let's take a look at another example where we do have more of a problem. F of x here is 2x to the 1/2. Now remember, that's the same thing as 2 the square root of x. So immediately I'm thinking the domain is going to have to be that x needs to stay greater than or equal to 0. Now g of x has that same problem. So domain, again, because this is the same thing as negative 6 the square root of x needs to stay greater than or equal to 0. Well, when we add those two together, 2x to the half plus negative 6x to the half, 2x to the 1/2 plus negative 6x to the 1/2, well, we just get negative 4x to the 1/2. So when we think about its domain down below here, again, x is a square root, so x needs to, or x, sorry, is under the square root, so it needs to stay greater than or equal to 0. However, when we multiply, we're saying let's take 2x to the half times negative 6x to the 1/2. Well, remember, multiply the numbers in front, and when you multiply with equal bases, we add our exponents. Well, a half plus a half equals 1. So we really just get negative 12x, which appears, well, hey, that's not a problem. I can plug anything I want in for x. I can multiply by negative 12 and still get a real answer. However, because the original f and the original g had limited domains, and really it only takes one of them because the original domain of f is greater than or equal to 0, the domain of our new answer is still that x needs to be greater than or equal to 0. Because we couldn't use the numbers at first, we can't use the numbers even in our final statement. Let's go ahead and try one more example and we'll see how that kind of comes together. Again, f of x is 4x to the 1/3. That's 4 the third root of x, which means that the domain would have been all real numbers. G, however, is limited so that x needs to be greater than or equal to 0. Again, remember that's the square root of x, x to the 1/2. So now when I go to find the quotient, or f divided by g of x, also written f of x divided by g of x, remember they're not multiplied, it's just saying they're both functions of x. I'm going to take 4x to the 1/3 and divide by x to the 1/2. Well, now remember, division rules say equal bases dividing means I'm going to subtract my exponents. So first I need to do a quick little bit of work here. 1/3 minus 1/2. Let's make them common denominators. So I'm going to multiply the top of this one by 2 and the bottom by 2. And the top and bottom here by 3. And end up with 2/6 minus 3/6 is a negative 1/6. Well, that means that my answer here is 4 divided by 1 is 4, x to the negative 1/6, or 4 over negative exponent's going to flip that to the bottom, and a 6th root of x on the bottom. So there's my final statement. Now the domain of that function has a couple of issues. First of all, we know that from g of x we have to be greater than or equal to 0. Well, that's still the case anyway because the 6th root of x also told us from the denominator and g of x for that matter, x needs to be greater than or equal to 0. However, also from the denominator, we know that x can't equal 0 or we'd be dividing by 0. Right? Thus, if x has to be greater than or equal to, but can't be equal to, our final domain then is that x just needs to be greater than 0. Combining those two ideas, that x needs to be a positive or 0, but can't be 0, means that my final answer just needs to be a positive number. I hope that helps you with composition of functions. Again, the basic idea is do the operation, combine them however, division, addition, subtraction, or multiplying, but then also think about their domains if it's requested in the directions. Good luck and have a great day.